Good afternoon, everybody. We'll start in a few minutes, maybe 1 minute. If you have any questions in the meantime, let me know. Okay, let's start. Last time we were together, probably a couple of weeks ago, we started to talk about how a programming language handles the flow of control. So the questions of when and how and in what order to do things so that we can achieve the semantics of the task that you actually are programming. And the first concept, unifying concept, was expressions. So we have seen that expressions and also statements, of course, we'll delve into a little bit in detail in the expression, context of expression, and then we are going to talk about a little bit more about statements when we talk about procedures and functions later on. Probably the next lecture 7 will be on those topics. Now, if you recall from expressions, the main theme was so when we kind of okay. Do you hear me? Am I still
yes, sir.
On? Okay. I think I might have a little bit of a network delay and network connectivity issues today, so bear with me. So we saw that if you actually separate these two things, what you do or how you control the flow into basic two components, statements and expressions, one returning value and doing no side effect, and the other one returning no value but achieving a side effect, then these two concepts, these simple concepts, can actually let us achieve a lot of things with regards to the control. Now, of course, that didn't have two pieces. One piece was related to functions and procedures when we want to actually modularize our programming into pieces and call those pieces for reuse and everything else, right? So what happens in those cases? What do we do as far as the flow of control is concerned? And we are going to come back to that the next lecture. And another topic that we need to, another problem or another thing that we need to handle is what happens if something happens unexpectedly. So we assume that certain things will go as expected, but especially because of the fact that a program is actually implementing a partial function, that would mean that for some values of input, there will be no output. So how do we handle that? And the topic for that is exceptions, and exceptions are kind of a way to control the flow of the flow in the case when something unexpectedly happens, and how you deal with this. Of course, this is now once we come to that point and understand that exceptions are done for that purpose. So the programming language designer has choices, and we are going to discuss what those choices are. One choice is actually offer nothing. So for exception, I offer nothing. Let's say C. C offers very, very, very, very limited things in terms of exceptions. And it says, okay, you handle it by yourself. So what a programmer needs to think about is those cases where, or let's say, exceptions are like part of your semantic. You have to handle it yourself. And some languages, programming languages says, okay, this might be too arbitrary, especially if you leave it to me as a programmer. I may make mistakes, and the user of my, let's say, anybody that uses that program or portion of that program may actually have trouble as well. So exceptions are reality. I mean, this is real. Exceptions are real. It happens. And if you leave it to the programmer to handle it, then you are putting too much on the programmer. So the question is, how do we actually somehow regularize this? Meaning make some unifying concepts or find some unifying concepts such that the tools that you provide in your language that you are designing may make this thing exception handling easier, more uniform, more reliable, perhaps. So this is now you would see very early languages, except probably functional languages, don't have a lot of mechanisms. Someone is, okay, please turn your mics off. I see an echo, I hear an echo. So some early languages didn't have these capabilities or tools, and new programming languages, especially after, let's say, Java and C++ and later versions of C++, and many other languages actually added capabilities or tools to handle exceptions. So let's review what those are. Of course, we are gonna look at this again from two perspectives. One is from a functional programming perspective, where all you do is evaluate expressions. And the other one is more towards the procedural or declarative, not declarative, imperative programming paradigm. Okay, so the basic idea behind exceptions is providing a structured exit from a program when something unexpected happens. Okay, you terminate part of the computation, you jump out of the construct, pass data as part of your jump because something happened. You have to get out of there, get out from your normal flow, and to do that, you have to pass some data so that wherever you are jumping to handle or jumping to, let's say, do something about the exception, you have to pass some context data. You pass context. In what context did this happen? Has this particular exception happened? And what is the state around which that happened? The context, the actual context. So this is passing data as part of that jump, and then returning to the most recent site set to handle this exception. So where are you jumping to? So how do you get which, how do you actually define and how do you find the code segment or code or whatever to handle this or some sort of control to handle this exception? So most probably when you provide a mechanism, there won't be just a single exception and single handler for an exception. So do you allow multiple handlers? And when you have multiple handlers, how do you bind these exceptions to code that you actually write with your whatever your language is providing. And unnecessary activation records in this case may be deallocated. So if you might have some sort of an activation record, some context that is kept during the actual construct without exception, and when you actually go from there, you may need to maybe free those or deactivate those activation records if they are not needed, and if they are not gonna be needed in the context to recover or to handle whatever that exception is called, is how that exception is caused. So this may require a need for some releasing some heap space or releasing some other resources. So exceptions, the unifying concepts around exceptions is actually there are two main constructs that languages are using. One is called exception handler. This is actually a declaration to establish these exception handlers. So how do you declare to establish your code segment or code that handles that particular exception or a set of exceptions? These are called exception handlers. And the second construct is a set of statements or expressions to raise or throw exceptions. So the basic idea is you say, okay, when do you, let's say, let, or when you encounter your exception, how do you change the control? How do you change the flow of control to exception handler? So this is usually handled by something called raise or throw. We are going to get into these two things. These constructs are usually they are actually designed to handle unusual or exceptional conditions, such as, let's say, an undefined function output undefined for a given input, a partial function, right? But this is not necessarily always the case. Sometimes these structures, these constructs, especially exception handling, might be useful to do some, let's say, a flow of control outside of these exceptional conditions. So when you give people some tools, they don't always use it for the reason that tool is created. Sometimes people find more creative use of those tools, and you might see in some cases where exception handling is not necessarily handling just an unusual or an exceptional condition, but is part of the definition of the semantic that you want to actually occur or implement in your program. So we have to be careful about that. Now there is an example. This is a functional programming language. We have been talking about this from time to time. It's called ML. And the way that actually it works is you define an exception. This is declaring an exception by name. So you say, okay, you have an exception called determinant. So this is the declaration part. You can think of this as a kind of a type definition. We are going to come back to this one. And then you have a turn your mic off, please, whoever that is. You have a function called invert, and this is from linear algebra. You have a matrix, and you want to invert this matrix. And we know that inversion process is not defined when the determinant of the matrix is actually 0, because there is a division involved. finding the inverse of a matrix, and when the determinant is 0, that matrix is not invertible. You cannot invert let's say non-full rank matrix. Okay, this is the definition of the function. So this is a partial function. So here, what ML provides is, it says, okay, it provides a check for you, and then when you actually catch that, so this is simply when your determinant is 0, what you are going to do is you have to let this thing handle that 0 case separately. So of course, if you leave it to me as a, let's say, without this mechanism, this exception handling mechanism, I would say if determinant is 0, then I would return something. But what am I going to return, right? If this is a true functional programming language, it has to return something. But what do I return? So the semantic is the implied semantic when I actually return something for a non-defined or undefined input is very critical here. So I cannot just simply return something for the sake of returning something, right? I have to return something that actually makes sense. And the question is, do I do this in my program, in my function definition? Like I would say, for example, if this thing is determined as 0, then return, let's say, the matrix itself. Okay, even though I know that this is not correct, right? So then this function invert is actually not achieving exactly what I want. It is actually giving something. And then maybe if I ask someone else to do this try this program or this function, they may decide that maybe, let's say, they return a matrix with all 0 entries. That's a possibility. And neither of them is actually correct because it's an undefined output. And I am choosing one specific output to be the answer, which is wrong. And the other person is deciding another possibility, which is also wrong. So the semantic of the function is wrong. Now, the question is from the perspective of the user of this function, right? Now, users looks at this and say, okay, if this is Jakub's program or function, I know that it's going to be returning me the same input as the input. The output is going to be the same as the input. If this is, let's say, Mehmet's version of the function, Mehmet is going to return the same size matrix, but 0, 0, 0, 0. All entries are 0. Now, then this invert function now actually is no longer semantically true because it can give me 2 different values. And if you recall from the very beginning, determinism is an important thing. A function called with the same input should not actually return 2 or 3 or different, more than one output. It should return only one. Now, putting an exception mechanism here, exception handling mechanism here, I can push this decision to the user of my function. I can say, okay, hey, this guy is going to throw an exception, meaning for some cases of the input, this function is not going to be defined. And I want you to know as a programmer or user of this, as a programmer and a user of this particular function, I want you to know that so that a partial function actually has 2 things, 2 outputs. One is a valid output. This is when there is no exception happening, and an invalid output when there is an exception happening. So these 2 things. Now then, the output of a function in this case, if you think about it, now kind of has 2 types. One is when everything goes fine, we have a matrix. The output is a matrix, which is true inverse of the input matrix. If something goes wrong, meaning that if the determinant is 0, then the output is now an exception instead of a matrix. And that exception has to be handled somehow. Now, the way that ML does this, being let's say, a functional programming language and taking these expressions for its true definition, it says, for example, here, inverts the given matrix, and then it knows that actually there is a possibility of exception here, and then it says, okay, handle this. Now, in this case, this handling is here, there are two parts. One part is, if this is right, this entire expression, this is an expression. This entire thing is an expression, which might have two values. There will be two cases. One is the case where the exception doesn't happen, and I return that matrix to you as a matrix type, and it has a certain value, okay? And then if the determinant is 0, then you have this other part here that you can define as a programmer. You can say, okay, if this handling is not, if there is an exception, now I make the decision as a user of this invert function, not you as a writer of that invert function, but me as a user of that invert function, so that now I know that invert is a partial function, and in the defined cases, I know how to use it. In the undefined cases, I know how to actually respond to it, meaning I can define my semantic here. I can say, for example, if you recall, a few minutes ago, I said, okay, if Jakub wrote this one, it will be returning all zero, or the input, the same input. Or if Mehmet wrote this one, he would be returning all zeros. Maybe now I can decide here what to put here. Not maybe, but now, as a user of this invert function, I am deciding what to do. Of course, now, this doesn't need to be just one level, right? It may be that I don't want to make that decision here because I'm writing another function which is using this invert, and I want to make this visible to whoever is going to call my function. Let's say this is part of another function, let's say f2, and this f2 function, I don't want to make a decision here, use this or that, or handle this way or that way. I may want to actually even push this one up, whoever is going to use this f2 function, to make that decision for them. But of course, what happens is that in that case, things get a little bit more complicated, right? So I had only one function, invert function, that was partial. Now I have a composite function that uses invert as well. And this composite function has is also a partial function. It's not a total function. Now, the question is, if the partialness is only coming from invert itself, then perhaps I can actually pass through to the caller of f2. But if this function f2 is also have additional partialness, meaning additional things that might happen inside f2, addition to this determinant being 0, and there are some other things that f2 is added into its definition as where the partial, so f2 is also partial, but not exact partialness of the invert, but some additional things or additional exceptions that happens. Now the question is, of course, how do we push these two things one level up? Whoever calls f2 may want to know where this thing coming from, or may not want to know. For example, f2 might be, let's say, simply a solution to a linear system. So things like, for example, a times x equals b. This is a linear system. And some solution to this linear system might actually do an inverse of A, if A is a square here, or otherwise you can also go for some other things. But of course, we don't do it this way, but assume that it is done this way. So AX equals B, the solution to this one might be the semantic that is actually, or the function that is put in F2, right? Now, inverse of A involves calling invert, and invert actually perhaps doing is actually having, in this case, might have an exception. Now, it may be that additional stuff in F2 has exceptions as well. Now, the question is, from the semantics perspective, whatever the semantic is here, do you actually say to your user of your function F2, do you say, okay, I am using also invert, and I want you to know about when invert fails, this is this way, or when invert doesn't fail, it is this way, and you might have essentially two types of exceptions handling, and which one you want to open to the caller of F2. In some cases, you may say, okay, inversion is my idea, meaning what I do as part of my semantic. You don't need to know about it. And then when it happens, I will tell you something. I will tell you that, okay, I cannot solve this system AX equals B, maybe. Or maybe I can say, okay, hey, I actually have two types of things here, two types of exceptions. One is because of the determinant, and maybe something because of, for example, let's say some other things, I don't know, whatever it could be. Then because of that, I want to actually let you know which one actually failed. So you define your exception semantics here and let your caller of your F2 actually decide what to do about it. So as I said, now at single level, this is easy to kind of grasp, but you might have multiple layers of these exceptions. Something that you depend on, you call, might have thrown an exception. And the question is, do you handle it yourself, or do you pass it to your, let's say, your caller, considering that you might also have additional exceptions to actually pass through. And now the handling mechanism kind of gets complicated, right? You have a nested structure. So these are all relevant problems with regards to how do you implement this mechanism and how do you actually keep track of things. So this, and if you're, let's say, if you have a block of code that might actually, or an expression, for example, you might have an expression like, let's say, in ML1 and then maybe 2. Let's say this way. This is not good. Let's see. So let's say you have 1, and then you have 2. No, this doesn't work. Anyway, so if this guy throws an exception, possibly, and if also this guy can throw an exception, both of them can throw exceptions. Now, when you evaluate this expression itself, this compound expression, then you have to be able to handle these properly. So this handling, which exception is handled by what part of the code, we are going to come back to in a few minutes. So, okay, in C++ has a mechanism for this one as well, like similar to ML. So you have, as you can see here, it's actually quite similar. What happens is that if something goes wrong, you throw this exception, very similar to before. You see that here, or otherwise you continue. Okay, and then the way that you actually call or handle it or call this function, it differs a little bit. You can see it here. You have a try block where you actually, as the name suggests, this statement tries this thing. And then if it doesn't, let's say, fail, or if it doesn't throw an exception, then you continue from here. Or otherwise, if there is an exception, you handle that exception here. This is the handling part. So if this part of the code actually throws determinant, you can catch the determinant here. Okay. We haven't talked about in either languages, in either of these languages, we haven't talked about what is passed from the call from the exception throw to exception handling. We are going to come back to that in a few minutes. C doesn't have a mechanism, an explicit mechanism for this one, but of course, you might be able to actually program something to the same effect, albeit it is a little bit, not a little bit, quite cluttered, as you can see here. So in this case, they are using this set jump functions here, and then you define your exception using enumerated type, and then when there is something happens and you handle that one and so forth. So C code, you can see that is quite cluttered with respect to the C++ code as well as the ML code. All right. Now, this termination semantics. So there is so the question is, what do you do at the handling site? And what do you do after handling? Do you continue, or do you actually terminate the program? Terminate the flow of control, meaning semantic actually stops there. And it's actually, okay, this is done. So this is from Wikipedia. You can read it through, but the basic thing is here is that exceptional handling mechanisms in contemporary languages are typically non-resumable. This is called termination semantics. Whereas most of hardware exceptions, we are talking about, of course, software exceptions. In the case of hardware exceptions, they are typically resumable. This is, again, going back to the von Neumann machine and so forth. So, this, of course, the decision, for example, for C++, the decision of this termination semantics are not come up with very easily. So this is a very contentious topic, having these termination semantics, non-resumable versus resumable programming. Both have problems, right? So if you resume, certain things are going to be very difficult to do. If you not resume, or if it is not resumable, then you have some easiness in terms of, let's say, handling mechanisms and so forth, but you might have, let's say, less flexibility in handling your let's say, partial functions. Now, from theoretical perspective, a partial function, this is the question, what do you have when you have a partial function? And how do you actually fill in the missing value for certain inputs? The question is, you can resume it from where you left. If it is, let's say, in a simple case, just a single function, if you can define universally acceptable, if you can find an acceptable definition of how you should actually handle those cases where output is not defined in the functional, with regards to a function. When you have like procedural languages or imperative languages, then like statements, then you need to decide what do you do with respect to the state changes. So every statement that you have will do some state change, and you have to decide on that state change. Now, functional programming from that perspective is a little bit easier to look at. Let's say if you have a certain acceptable definition of those exceptions accepted by, let's say, your community, then you can actually handle it a little bit better, easier than compared to imperative languages, because imperative languages, the problem with, or at least from this perspective, the problem is each statement actually does something to the state. It does have side effects, and side effects is defined by how you, in what order and how and when you execute those statements. And then when something happens in the middle, something bad happens or something unexceptional, unexpected happens, then you need to actually understand you need to track what type of side effects you have done. And then you need to have an acceptable mechanism to say, okay, this is how I recover from that. And this has to be accepted by everybody solving the same problem, let's say. And it is more difficult to do that in imperative languages than functional languages. There are opposing views. Some say, okay, this is again heavily related to the types, right? So even let's say an exception return function will have a type, and this semantic that you actually, the thing that I said, okay, if you have an acceptable solution by everybody to those exceptional cases, then you can do this one. You can resume, or you can, let's say, you can terminate, or you can resume, but if not, you can terminate. So that, okay, I'm gonna read this one. It says, okay, many of unnecessary, like whatever for exceptional handling. He finds exceptional handling very, very dangerous. He says, do not allow this language in its present state to be used in applications where reliability is critical. Why is it critical, reliability here? Why is it critical? Because again, if you are, let's say first, if you are terminating, that termination, I need to actually know when it is going to terminate. I need to find out all these conditions that can actually terminate, and I need to find a solution, what that termination means, how I continue, right? And he says, okay, if you are maybe if you are sending a say a probe to Venus, it may not be a big deal. You just lose your let's say work if this happens. But if this is a nuclear warhead and it explodes somehow because of these exceptions over a city, then this is a very, very bad thing, of course. So the reliability, if you want to guarantee reliability, these type of mechanisms actually put a lot of loopholes, a lot of booby traps, puts a lot of stuff, a lot of let's say paths in the control flow of control that you may not actually know where it is actually going. And enumerating that might be very, very expensive from software engineering perspective or testing perspective. Therefore, the reliability can actually can suffer. Whereas if you actually force resuming, this is what the hardware people do. They somehow force resumption. And if you actually know how it is going to be forced to resume, then maybe the flexibility is not going to be there as much, or you are going to actually do a lot of extra work to resume, but you can have better reliability on such a case. So this discussion is still ongoing, and it is going to go for a long while. So, for example, these guys, Weimer and Nicola, they say there's exceptions. They create hidden control flow paths that are difficult for programmers to reason about. I mean, you are already implementing probably something, a semantic that is very, very difficult to grasp and test and so forth. Now you are adding on top of it these hidden control flows that is not obvious in the program. When I look at it here, this is not very obvious. It's not very obvious here where my, let's say, control is actually changing. So I have here this try block, and I know that there is something, there might be something happening here, but I don't know. So this, there are three paths, there are several paths here. One path is invert doesn't cause anything, and I continue here. This is the first path, and then inverts cause something, and this is the second path that I take, and then I continue. Now, this is in a simple case when you have only one exception within your block. When you have multiple exceptions, this is going to be combinatorially, this thing is going to be actually multiply, and your tree, that path, that branching on the path is going to actually multiply as you have more and more of these things. And especially if you have dynamic binding that binds to, let's say, binds one of whatever is thrown there, then you have a very complicated paths that probably will be very difficult for programmers to actually reason about. So this is, again, is important. Now, you can say, okay, perhaps just don't put it there. Don't handle exceptions. And then the alternative is very bad as well. The alternative is what we see here. Now, perhaps these cases here, these branches, you need to now know all of it anyway, because you are designing it now. So this is not hidden, and it is made explicit by you to handle these cases. So it's just a matter of actually asking who is going to do it. Now, if you say that, okay, if I want to actually do this resumable, then we need to talk about all these possibilities of actually how to undo things when we throw the exception, and then how to resume from the exception going back. Now, in a hardware, this might be a little bit easier because the functionality is very limited. The functions that you implement in hardware is very few compared to almost an infinite amount of, let's say, functions or cases that you can actually generate with reasonably, let's say, expressive language like C or whatever. All right. So this is this question is not resolved, and this will continue. Now let's look at actually what are available for us to actually do. So we distinguish between two classes of events. Those are that are detected by hardware. This is one possibility, and the other one is the software detectable problems like subscript being out of the range of an array, subarray, whatever. We have some terminology and definition. An exception is an unusual event that is detectable by either hardware or software, and that may require special processing. And the special processing in this case may be required when exception is detected. Is called, this is the special processing is called exception handling, and the processing is done by a code unit or a segment called exception handler. So handling this special case is exception handling, and the code or a segment or a procedure or whatever it is that does this thing is called exception handler. And an exception is either raised or thrown when an associated event occurs. Okay. So user-defined exception handling, when a language does not include specific exceptions, exception handling mechanisms, then the user often handles software detections by themselves, right? This is typically done in one of three ways. One is use a status variable or a flag, which is assigned a value in a subprogram according to correctness of its computation. This is using standard C library functions. Use of a label parameter in the subprogram to make it return the different locations in the caller according to the value of label. This is mostly used in Fortran. And define the handler as a separate subprogram and pass its name as a parameter to the called unit. Okay, so this is another possibility. This is a little bit more evolved than the first two. Okay, so this is if you want to do this in a programming language like C and Fortran, where there is no explicit exception handling mechanism. When you have built-in mechanisms for exception handling, the advantages are such that without a built-in exception handling, the code required to detect error conditions can considerably clutter a program. So this is the biggest advantage, one of the biggest advantages of actually having built-in exceptions, that you may be able to do the same thing with, in a very simpler way than if you want to do this by if you want the user to do this programming. And another advantage is that when you have, let's say, a thing like this here, having another, let's say, if you want to change this code and add another exception handling mechanism to this one, so you don't have just, let's say, determinant zero exception, but you have another exception, then your program is going to get more and more complicated. Whereas a built-in mechanism might actually, if it has it, might actually help or allow exception propagation, so that, for example, you may not want to actually handle the, say, the exception at one location, maybe your caller, maybe not even your caller, but your caller may also pass it to the other caller, or the other caller may pass it to the original caller or whatever. So this is a possibility. So in this case, an exception raised in one program unit can be handled in some other units, or it could be dynamically or statically defined ancestry by its ancestry. So in this case, for example, you can have a single handler that can be used in different locations, right? So you don't need to actually have everything, multiple handlers doing the same thing in this case, if you are able to, of course, propagate exceptions. Okay. Another advantage is building exception handling forces the programmer to consider all the events that could occur and their handling. So what, of course, if you do this properly in the language definition, so if something is thrown, your programming language may actually enforce the handling of that thrown exception or possible exception. So this way you can at least ask the user to think about and act on it, act on it such that a corresponding handler is actually written. Of course, this doesn't mean that that handler is going to be correct. So you cannot guarantee any semantic here, correct semantic, but at least the language construct, this construct in the language that you have, may actually force the user to think about it. Of course, again, that thinking can have loopholes in it, but anyway. So this is better than, of course, not thinking about it at all, right? So another advantage is this type of exception handling can simplify the code of programs that deal with unusual situation. So this is very similar. So we have seen this. Now, there are some design issues that we have to handle now with regard to exception handling. So there is a simple example here. we say, okay, there is a sum divided by total, and this, when total is 0, this might actually return a hardware exception. And this is the exception handler that actually does this. Okay. Now, what are the exception handling issues? The design issues in exception handling. The first one is a binding. So binding the exception occurrence to an exception handler is the question here. So an exception happens. Now the question is, which handler is going to handle this guy? So there are two possibilities. One is at the unit level. So in the same unit as the exception happens, how can the same exception raised at different points? This is the question here. How can the same exception, let's say division by 0 exception, I have 4 different places that this can happen in the unit. How do I actually make sure that these different points in the unit is bound to maybe different handlers or maybe the same handler? How do I actually bind that? So this is at unit level, multiple exceptions happens, same or different. And then I want to actually be able to answer the question, which handler is actually handling which? So this is the binding. Another possibility is at a higher level. So assume that you have a function, the unit level, and you don't want to handle it in the unit level, right? So you want to handle it outside your unit level, as we have been discussing. I don't want to do this invert function, let's say, stopping there. I want this to be handled, whoever is calling that. The calling unit should handle that. So in that case, if there is no exception handler local to the unit, so I may actually pass that. Should the exception be propagated to other units? This is a question. This is a very, nice thing to have, of course, but not easy to handle. How do you actually know now or enforce or bind? The binding is not actually easy here because there will be a lot of paths. This can, let's say, this will require some searching in your runtime, or maybe some of these can be decided on statically, but mostly it's going to be most probably dynamic. And in the dynamic case, you have to actually decide when to, which one is actually associated with which one. The question is, of course, not just do I allow this to happen, meaning at a higher unit level, I can catch or handle the exceptions. And the other question is, how far can I go? How many levels? How many ancestry levels? So if let's say, if I force the handlers to be local, then what may happen is that I may need to write a lot of them doing the same thing, perhaps, right? So division by 0, for example. I may want to actually have one handler for my division by 0. But I cannot put this one in a unit level. Let's say my function 1 has this, and then my function 2 will have the same thing, and so forth, right? If propagation is permitted, then the handler may need to be actually too general to perhaps to be really useful. Maybe there is another problem. So if I'm saying, okay, I want to handle my, let's say, division by 0 by one segment of code. Is this the right thing? Because there are so many things. What can I do? I can only stop, right? Or I can say, okay, now this is the question that we were asking in the beginning. Maybe in some cases when we want to assign a consistent value as an output to an undefined input, or a partial function that doesn't have an output for a given input, right? Then this might actually be fine, because I have a, let's say, at least in the entirety of my program, I'm handling everything the same way. Hopefully others are also handling it the same way, but this is not necessarily let's say, true for especially imperative programming, when I have done, let's say, a lot of state changes, and one path might actually mean something different than the other path. So the same code may not be able to actually handle this entire thing. So these decisions, these design issues, you have to answer. The other issue is the continuation. We discussed this one. There are two options. You can terminate. This is the simplest solution and often the appropriate one. You may also go for resumption, resuming wherever you have left off. This is useful when the condition encountered is unusual, but is not erroneous. There is no error, but it is unusual. So you may be able to actually do these type of things. In this case, some convention should be chosen as to where to return. Whenever this happens, what do you do? At the statement that raised the exception, or at the statement following the statement that raised the exception, or at some other unit. There are some other things, for example, finalization. Finalization is the ability to complete some computations at the end of execution, regardless of whether the program terminated normally or because of an exception. Do we have this support? This is the question. Do we finalize? So at the end of the exception or without the exception, I want to be able to actually complete things. Perhaps I don't want to, for example, so I have a division by 0 in my rocket going somewhere, and I don't want to just say, okay, exit 1. This is probably not a good idea. I want to be able to at least maybe turn off the, let's say, something so that when it lands somewhere, it doesn't kill or it doesn't cause damage. Right, so these type of simple things. So how are the user-defined exceptions specified? This is another thing. There are multiple ways of doing this. Are there predefined exceptions? This is a good question. Do we actually, does the language, like built-in types, do we define predefined exceptions? Common things that actually happens a lot, and I want to actually be able to just use them. If something happens quite a bit, why do I actually let the user do this as a user-defined thing, but why not making a, let's say, built-in exception? The other question is, should it be possible to disable predefined exceptions, for example, if you have a predefined exception? Now, this is a good case. For example, you might not have, let's say, a division by 0 problem because you know the input space. You accept, as a writer, programmer, you may know your, let's say, the input space, even though your function might be partial for all definitions. You may guarantee yourself that undefined outputs or undefined outputs for some inputs, those inputs may never happen. So I don't know, for example, if you are, let's say, reading the age of a person and dividing that, use that as a divisor for something. So you don't care, most probably, and if those are, let's say, I don't know, working age people, you know that there will never ever be, let's say, division by 0 there. Now, if you have a predefined exception where whenever you have a division, you ask the user or the programmer to handle that. Make sure that it is actually gonna be handled, no matter what. But I know I'm never gonna get it because I'm controlling it somewhere else. But division by 0 exception doesn't know about it. It wants to actually enforce it. Now, if I know that it's not gonna get ever there, but my language is actually forcing me to do that, at least add a few lines of code, maybe even just as simple as an empty, let's say, function or empty, let's say, block. It's still a work that I need to do, and I may not want to do it because, again, I have guaranteed that that will never happen. Now, in these cases, I should be able to actually predefine let's say, disable these predefined functions, or not functions, but exceptions. Now, but there is a danger with this one. Why do we put this one in the first place? Because we want to increase reliability, right? And now I'm able to actually turn them off. When I'm able to turn them off, some lazy programmers or maybe malicious programmers will actually turn them off. And now the basic idea of forcing to think about these type of exceptions to improve the reliability to reach the correct semantic is now gone. So then why bother? So these type of questions has to be answered. Another one is, if there are predefined exceptions, should there be default exception handlers for programs that do not provide their own? Maybe I want to actually provide default exception handlers for those predefined ones. So always do this. When there is a division by 0, always do this one, unless the programmer overrides it. Now, this overriding is, of course, another issue. It's going to be another design choice. Can a predefined exception be explicitly raised? Can I actually just say, okay, instead of it is implicitly raised, can I explicitly say, okay, throw this exception now? To do what? I don't know. Maybe some semantic requires that, but this is another issue that you need to, or another design issue that you might want to actually have an answer for. And then hardware detectable errors. Are they treated as exceptions that may be handled or not? So these are things that you need to answer. Okay. Let's okay, oh, it's already 3:01. Let's take a 10-minute break and we'll continue from here. All right, so let's look at how Java does it at least very quickly. Java has, similar to C++, this try block and then multiple catch blocks. A try construct includes a compound statement and called a try clause here, and a list of exception handlers afterwards. So an exception is thrown using the throw statement, like this one, for example, throw new my exception, something like this. And then in the binding, what happens is that if an exception is thrown in the compound statement in the try block, try construct, it is bound to the first handler following this try block, and this is the catch function, immediately following the try clause whose parameter is the same as class, same class as the thrown object or an ancestor of it. So it needs to match type-wise to the parameter. So here, these formal parameters of these catch blocks here, if there is an exception raised here, and the type of exception is going to be matched to this guy. If it is matching, then it will be handled by this one. Otherwise, it will be looked for the second one and third one. This type of a kind of, in this case, this is not a pattern matching. This is a type matching. So a class has to match, or it has to be either the same class or an object from the same class or an ancestor of it. So if the matching handler is found, then throw is bound to it, and it is executed. They're very simple. We discussed this finally in the additional issues, the design issues. So Java has the final clause, and this occurs when, for example, in the case where a file must be closed or needed, when a file must be closed or an external resource is released, regardless of the outcome of that try block, be it just happens without an exception or with an exception. So finally, clause at the end of the list of handlers can help, is the structure to do this one just after the complete try construct. So the final clause is executed in all cases, whether or not try throws any exception, or whether or not it is caught by a catch clause. There is a similar topic which is called event handling, and event handling is kind of similar to exception handling, but not exactly the same thing. It is a kind of programming, say, construct. The difference is that while exceptions can be created whether explicitly or by user code or implicitly by hardware or a software interpreter, events are created by external actions, such as, for example, user interactions through a graphical user interface, like a mouse click or clicking on a button or whatever else you can do. In event-driven programming, parts of the program are executed at completely unpredictable times, often triggered by user interactions with the executing program. But here, this is the event-driven programming, so it should not be confused with the exceptions. And these are all resumable things. They are not unresumable. These are not exceptions, actually. The only thing that happens here is that you don't know which event is going to come, first, and you can use similar techniques to just, for example, wait for an event to happen and then have a pattern, a set of patterns that looks for which event is actually happening so that you can actually handle that event according to your semantic. ML has this type of exception handling. It has a declaration, very similar to a type declaration. It has exception, name, and it will have type. An exception can have a type. Gives the name of an exception and a type of data passed when this exception is actually raised. And the raising up happens with a raise command like this. Raise the name of the exception and the parameters to be passed to that to the handler. And the handler is you have exception. You have this exception expression. Sorry, you have the expression. You have the handle and the pattern matching the raised exception. And then so if this expression doesn't cause any exceptions, then the result of the value is going to be this thing, the resulting value of this expression. This whole expression is going to be the result of expression 1. If it happens to have an exception, and depending on the pattern that you put here, this particular pattern is going to catch or bind to an exception that happens in expression 1. And once this is happening, then the result is going to be the entire thing, this entire statement, not statement, expression, will have the result as this expression 2. So evaluate the expression first. If exception that matches pattern is raised, then the value of this exception, this expression is indeed the value that you will get from expression 2. So there is an example here. It defines the exception as overflow. No type is defined here. That means that there is not gonna be any parameter passed between the handler or from the throw to handler. You have a function, a reciprocal function here. If x is less than minimum, then raise or flow, else the answer is 1 divided by x. So this is fine. This is a function that can generate or throw an exception. Now, the use of this thing is going to be here. This is the critical part. So you call the first expression is, your expression is this one. You want to actually get the reciprocal of x, okay? So the reciprocal of x, if x is smaller than minimum value, then there will be an overflow. And the overflow is this guy here. Now it says, okay, if this is matching after call to reciprocal x, then I want to generate 0 as the overall value of this expression. So if reciprocal x doesn't generate anything, any exception, then it will return 1 divided by x, right? So this is fine. So for example, reciprocal 1 will say, okay, it will be 1 divided by 1 is 1. There is no exception thrown. Therefore, the result of this expression is going to be, so R1, if this is 1, then the result of this expression, this entire expression here is going to be just 1. If it, let's say, if it was 0, this is the interesting case, then reciprocal x, you can look at here, if x is less than some minimum, let's assume that minimum is a very, very small number. It's a 10 to the minus 28, let's say. 0 is less than 10 to the minus 28, then raise or flow. So now this thing is going to catch that. This is a pattern that will match it. And then it says, okay, if this is the case, then I will return 0. So R0, this R0 handle overflow 0 is going to give me, in this case, the value 0. Whereas this one, this is another one, you can see here, this is the same thing, y. And I look at y, I say, okay, y is, let's say, 0, right? If y is 0, handle overflow matches here. And then in this case, what happens is that the entire, this within parentheses, this entire expression returns 1. And because reciprocal actually 0 has thrown an exception. Now you can see here that I can actually take this structure, this exception mechanism, and handle it in 2 different ways. In one case, I am actually saying that something divided by 0 is 0. In this case, on the left-hand side of this division here. Whereas when in this particular case here, what I say is that if this thing is actually y, if this is 0, then I will actually return 1. So this means that 1 divided by 0 in one case is 0, and in the other case is 1. This is the definition that I actually, as a user of the semantic, the way that I handle this is actually this way. So you can handle, you see that this is true functional programming, and you have a expression, and an expression can either have a defined value for that function or an exceptional value, which I define by myself as a user. So this is quite useful. Of course, you can do the same thing with Java or C++. Now, the other thing is that if there are multiple handlers, so you might have, let's say, multiple of these things can match actually. In this case, you jump to most recently established handler on runtime stack. So this means that actually runtime stack actually will go this way. And if you have a handler somewhere, it will be actually on the stack, and in the right stack. If it is in the right stack, then in the stack, then you start from the top of the stack and you go down to find your handler. So this is the way that ML handles scoping. Whereas, for example, you have seen that in Java, the scope can be defined statically. Not statically, but at least the order is written in the written order, right? So it's similar actually in a way that you can say, okay, the first pattern or first catch might be in the on the top of the, let's say, stack, but the handling is a different is done in a different way. So this type of scoping is not, of course, accidental. User knows how to handle error, so you want the user to actually define the order of which these things are actually going to be handled. And author library function doesn't know that. So the reciprocal function author, let's say me, I don't know how you are going to handle this thing, how you are going to know this one. So that I will let actually you to handle it instead of me handling it for you. All right. So I'm gonna pass these, and this one mostly, okay, maybe. Okay. So you can, the way that this the scoping of static or dynamic scoping of actually binding, you can read through this. This is not that important. We have covered the basics. So one of the things that is a little bit related, and I don't know, I couldn't find a good place to actually put this, so I am actually covering it here, is the garbage collection. So this is, if you recall, maybe a month or so ago, we discussed memory management and especially the heap management. And so heap needs to be managed, and a programming language has to have some certain mechanisms to do this one. And the reason that I put it here is especially this resuming from given let's say exception is actually requires and first going to the exception and coming back from the exception and so forth requires the volatile or states to be actually managed properly. So this is why I'm covering it here. As you recall, we have 3 parts of the memory: the stack area, runtime stack area, and the heap, which is a fixed size variable content area, and dynamic allocated objects and data structures. And the way that actually people manage this heap is with a few simple concepts. One is a cell. A cell is a data item in the heap which is allocated. Cells are pointed to by pointers held in registers, stack, global, or static memory, or in other heap cells. So this is a cell is a data item in the heap, and the way that you can access to a cell is a pointer, and this pointer a reference, and this pointer can be either on a register or on your stack at a given time, or in your global or static memory, or perhaps also in another cell in the heap. So this is the first thing. The second definition is roots. These are registers, stack locations, global static variables. So anything that is not on the heap, these are called roots. So this means that these are going to actually, of course, most probably going to have the pointers stored in them. So as the cell is live, then another definition, a cell is live, meaning it is active. If its address is held in a root, in one of the registers, stack locations, or global static variables, or it's held by another live cell in the heap. So 2 possibilities. One is a live cell has a pointer in one of the roots. The address is actually contained in one of the roots, either registers, stack locations, or global or static variables, or is actually held in another live cell. The other has to be a live cell. So very simple. In that case, a garbage, meaning an unnecessary, unusable heap cell, is a block of heap memory that cannot be accessed by the program. This is what a garbage definition is. So an allocated block of heap memory does not have a reference to it, meaning cell is no longer live. And another kind of memory error is a reference exists to a block of memory that is no longer allocated. So there are 2 possibilities, error possibilities. One is a dead cell, or a not live cell, or a reference exists to a block of memory that is no longer allocated, or maybe used for somebody else. Okay, and garbage collection process is the automatic management of dynamically allocated storage. This is very simple. So what it does is it reclaims unused heap blocks for later use by the program. So examples of garbage, you can see it here. So you have a class node integer value node next, and then you have node P and Q. And P has a new instance of node, Q has a new instance of node. So when you have this new class statements, what they do is they actually go to the garbage collector and say, okay, give me a heap, give me a memory. This is the memory that's allocated for P, and then this is for Q. Okay, and then it says P address is actually stored in Q's address. Now, when P is actually referring to this guy, now this guy is no longer live. Why? Because there is no root or live cell that is pointing to this guy. So this was, P was, you can see that P and Q, they are roots. Why? They are going to be local variables. So in the stack, they're going to be allocated on stack. So therefore, P and Q, whatever you store in P and Q in this context is going to be available as one of those roots. Okay, so when you actually do this guy here, you are taking one of your new node that is allocated in heap, and the address is stored in P, and the address is stored in Q. But later on, you decide to change Q's address by P, whatever the P is holding. Therefore, this guy is no longer live because nobody is pointing to this one, or nobody has an address that can actually reach this guy. And when you delete P, there is another thing. And you have to be careful, of course, with this one, whatever this operator or function is doing or statement is doing. This statement is actually, when it says P, most probably it is getting rid of this guy. And then it is also probably saying that P is now null. Its value is null. And when you do this one, Q is no longer actually, Q holds an address of originally P, wherever the P is pointing to, and Q is no longer active, or Q is no longer, whatever address Q has is no longer available to it. Okay. So this is a simple case. So why do we need a garbage collection? We have a lot of memory, yes, but we mismanage it. Memory leaks, dangling references, double freeing, misaligned addresses, null pointer dereferencing, heap fragmentation, and all these things are bad things for heap. Okay, and poor use of reference of locality resulting in high cache misses. So these are all related to the fundamental architecture, of course, but so if you don't have the right locality in an array, for example, or in a let's say a linked list, then if your linked list is all over the place, one piece is here, another piece is here, another piece is here, and they don't fall into this reference locality, then every time you actually access one of these, you are going to actually do a paging operation on the hardware that will actually complicate your runtime and will be very inefficient. So because of these things, what people try to do is explicitly manage these memory, or explicit memory management breaks high-level programming abstractions because all this possible mismanagement. So instead, they say, okay, if you want to be, I mean, we want to our programming language to be, let's say, high level and abstract things from us. And in an ultimate case, I don't want to know locality of reference. Why do I need to know? I'm not, let's say, interested in paging and all these things. Of course, as a computer engineer, we have to know this because we'll not always have a programming language that actually can do this management for us. But for I don't know, for let's say high-level programmers, they may not need to know this one, and it may be okay. But we are seeing here that we want them to know it. So this is not good. So a garbage collection can help us here. There is a discussion around is garbage collection a feature, a language feature or not. Most people say no, it's not a language feature, but it's a good tool. Garbage collection is a pragmatic concern for automatic and efficient heap management. Some of the cooperative languages in this regard are Lisp, Scheme, Prolog, and Smalltalk, and some uncooperative languages are from the garbage collection perspective is C and C++. But you have C and C++ have these libraries that can actually help you manage these type of things as an add-on. Object-oriented programming languages, especially Java, has garbage collection. And functional languages like Haskell and ML has a certain capability for this as well. So what is a perfect garbage collector? First of all, there should be no visible impact on program execution. So if I run my program a million times, let's say finding the root of a polynomial, it should actually do this thing in the same amount of time as if the algorithm is actually telling me that it has to do it at the same time, or the same amount of time. It should require the same amount of time. So if one run, for example, is stopped and there is a garbage collection happening in the middle, and the garbage collection takes 2 seconds, and then that means that there is a visible impact on my program execution. Another feature for a perfect garbage collector is it should work with any program and its data structures. So I shouldn't worry about, my garbage collector is not gonna work if I have a cyclic data structures, meaning a data structure that actually, let's say, a linked list or a cyclic linked list or something like that. It should collect garbage, and only garbage, very quickly. Of course, you may want to have this done incrementally to meet the real-time constraints. You should have excellent spatial locality of reference. So this means that whatever I am actually creating on the heap should allow me, especially, let's say, of course, this is a little bit difficult to achieve, but the consecutive, probably at least, the consecutive allocations should be on adjacent blocks or adjacent, or let's say on the same page, or maybe in next page and so forth. So it should not cause excessive amount of paging, and shouldn't cause any cache effects. So, and then it should manage the heap efficiently, meaning it should satisfy an allocation request and does not fragment. Fragmentation is also a big problem. So there are several algorithms I'm going to go through very, very quickly. One algorithm is reference counting. What it does is actually directly keeps tracks of live cells, and garbage collection takes place whenever heap block is allocated and doesn't detect all garbage. This is a kind of a disadvantage of this method. And there is another one, tracing. Garbage collection takes place and identifies live cells when a request for memory fails. The SPIC algorithm is actually either mark and sweep algorithm or a copy collection algorithm. And one of the problems with tracing is, of course, it requires time to actually do this thing. So it may actually cause stop and gag type of impact. And then there are some modern techniques that actually does this hierarchically, called generational garbage collection. So reference counting is very simple. What you do is you count how many you have actually additional bit of information on your block, on your cell, and then it actually says how many times or how many actually root sets are actually and also other sets is referring to it. So for example, here there is only one guy referring to this one, and this one is one, and this one is one, and this one is two, right? Okay, so you have this information. Simply you count the number of references to a cell. This requires an additional space and time overhead to store the count and increment each time a reference or a different dereferences is actually done. Reference counts are maintained in a real time, so no stop and gag effect. So this is done on the real time, and it is allowing you to actually do a incremental garbage collection, meaning when this number actually reaches the 0, then you know that this is done, and then you just remove it, and then you remove also the ones that you are referring to if there is any. Okay. The spatial locality of reference is reasonable here. access pattern to virtual memory pages no worse than the program itself, so no excessive paging. And it can reuse freed cells immediately. Once you actually know that there is you have a zero count, then you can actually do it right away. So incremental, relatively easy to implement, can coexist with many manual memory management. So you can actually add this to manual memory management. The weaknesses are space overhead, 1 byte, maybe I don't know how many bytes you need. Some sort of a counter is actually required. You have a time overhead. Each time you actually do this one, you have to decrement and check to ensure that it's not a self-reference, decrement the count to the old cell, possibly deleting it and so forth. So this is every time you do an allocation, you have some overhead that you have to actually do. And once one missed decrement results in a dangling pointers or a memory leak. So this is very bad. And cyclic data structures may cause leaks. You may not be able to handle cyclic things, like here, for example. There must be, probably there was a pointer here. This is done. And once this is done, actually, this looks active in this case, but because of the cycle, but this is not reachable by anybody because there is no root set that actually, these two cells locally are, looks like they are live, but they are not live. Okay. So this is similar to actually the smart pointer in C++, in ANSYS C++, which version I don't recall. So this is one of those libraries that actually provide this. The mark and sweep collection algorithm. Okay, I have 10 more minutes. Now, mark and sweep is a kind of a batch algorithm. First of all, each cell has a mark bit. There is a bit, just one bit information. There is a mark. Garbage remains unreachable and undetected until heap is used up. So you don't do anything till heap is full. Then you say, okay, now heap is full. I need to actually go through the garbage, throw them out. Hopefully, there are a lot of garbages so that I can actually open up some space and use that. Okay. In this case, garbage collector goes into work, and while the program is execution is suspended. This is a problem that we are going to see. There are two phases. The marking phase, starting from the roots, set the mark bit on all live cells. You just go start from the start the roots, wherever you have the pointers, and then you follow the pointers, and wherever you can reach, you set the mark bit to 1. On the sweep phase, of course, in the beginning, you set them to 0, and then you set them to 1. On the sweep phase, you return all unmarked cells to the free list. Whatever you have those unmarked bits 0. So those are garbage. You can actually remove them. And then you can reset the mark bit on all marked cells to 0. So that unmarked, so that next time when you actually mark them again, the ones that actually are not used anymore or live anymore, you can have them actually removed. So in the heap space, you have everything this way. Let's say this is the exact thing that you have. Then you start actually marking them. So in the beginning, everything is marked 0 because reset after the last step of the garbage collection. Now you mark them. You mark this one. You mark these because they are all reachable by your root set, from the root set somehow. So this guy is directly reachable, this guy is directly reachable, and there are two things. This is reachable, and then from this one, directly reachable twice, and reachable once. And these two are not reachable anymore, so they are going to be actually unchecked. And then now these are ready to be discarded or get into the empty cells or empty heap, and they are garbage collected. So this is a basic algorithm, very simple algorithm. The good side of it is actually the handle cycles correctly. doesn't worry about the cycles. And no space overhead, just 1 bit. This is a very, very simple thing. It's a very, very small, let's say, a portion of the memory is going to be set, and then and also the setting information is very, very simple, right? So just 1 bit. The bad thing about this algorithm is normal execution is suspended to actually let you do this thing. So you are in the middle of calculating your, let's say, your route to, or you are in the middle of actually calculating, let's say, if you need to take an action on your autonomous car, should you actually drive or stop? And then it says, okay, hey, I need to actually garbage collect, wait for me. And when I am done garbage collecting, you can actually resume your process. So this would be too late for an autonomous driver, right? Autonomous driving. May touch all virtual memory pages. This is another problem with it. So again, related to the first one, what you need to do is if these things already are separated, let's say if it is all over the place spatially, you need to touch these things. So reading is one problem whenever the memory management is concerned, right? So you need to actually read it, meaning you have to cache it, and then if you need to cache this, let's say, page, and this page, and this page, and maybe, I don't know, maybe this page, these are the same page, let's say, and this page, then you need to, let's say, in this case, you need to go through almost the entire memory to read these bits, and then also write these bits. You need to write them, and writing is more expensive. Reading involves just one load to the memory from disk, if you are using some virtual memory. But writing involves actually writing it back to the disk, which might be quite expensive. So this may lead to excessive paging if the working set size is small and the heap is not all in physical memory. Another problem with this one is that it may actually fragment the memory, meaning you might have your heap might be used, let's say, one portion here, another portion there, another portion there. And there might be, let's say, gaps that sometimes are not long enough. So in truth, you might have, let's say, 1 gigabyte of memory left, but your memory is so fragmented, meaning your live cells are so spatially distributed so badly that there is no consecutive, let's say, memory bigger than, let's say, 10 megabytes. And that might be actually a bad thing for you. So you have a 1 gigabyte memory, but you have only a 10 megabyte space that you can allocate because of the fragmentation. So to overcome some of these difficulties and make some of them worse is a copying collector. You divide the heap into from space and to space in 2 pieces, and you have cells in your cells in from space are traced, and live cells are copied into the to space. To keep data structures linked, you must update pointers for roots and cells that point into from space and so forth. So you have to be careful with this one. And only garbage is left in from space. You don't need to worry about it. So you just discard everything in the from space anyway. When the space fills up, the rows flip. So when the to space fills up, then you go and flip them. Now to becomes from and from becomes to. So there is an example this is from space, this is to space. I have this data structure. I start from the root. I copy one here, another one here, and so forth. Now the advantage of this one is, of course, I have to update these links. You know that actually these links are no longer the same. So these links have to be updated. So there is quite a bit of copying and updating those links. So a lot of writing to the memory. When you flip it, you can done. Now the good side of it is that actually very low cell allocation overhead. So out of space check requires just an address comparison. can efficiently allocate variable size cells and so forth. And then it is compacting, meaning the fragmentation is not there anymore, and good locality of reference can be achieved. Because especially if you are following, let's say, from root to this guy, and then root to this guy and this guy. So this will be probably the way that you would access your data. So this is a natural, the spatial locality is going to be somehow natural in this particular case. So it will follow the data structure that you have. Of course, the bad part is you have to split your memory into two pieces and you can only use one piece. So half of your memory can be active at any given time. The other is actually going to be unusable. So if you have a 64-bit architecture, then, I mean, not counting the paging, this might be okay. So your two space might be actually on the disk. So you might actually do the first one. So your from space might be on the memory, and you can actually swap them. Of course, there will be paging issues, but that's okay. All right. And there are generational garbage collectors. The idea here is that most cells die young, and they die young. Meaning, if I have so the way that you actually use memory is you allocate something, you do something with it, and then you just deallocate it. Okay, so when a cell is no longer live, it means that probably it didn't live too long. It died very young. So you can use these type of let's say heuristics to improve you can actually decrease the overhead of the mark and sweep or this copying algorithm. So what they usually do is they put let's say 3 generations in this case, an oldest generation, a middle generation, and a youngest generation, and then you do this copying method, and then you know that this is gonna happen quite a lot, and this is not gonna happen that much. So when you actually look at your algorithm, when you need to do a garbage collection, this will happen more often, and this will happen very, very infrequently. So if this is spatial temporal use of this thing is going to be what this generation based algorithms are actually doing. Okay, so this concludes. Okay, 2 minutes or. This concludes this topic of exception handling and garbage collection. Even though garbage collection is not considered by many as a language construct, but it is nonetheless an important thing to know about. And if you at least know that a language is, let's say, doing garbage collection and using generational algorithm, and you know what it means now. All right, perfect. Any questions?
Hocam ben bir şey sorabilir miyim?
Tabii ki.
İkinci anlattığınız şey vardı ya, bu herhalde sonuncusu. Geri alabilir misiniz slaytı biraz?
Copying collector or mark and sweep?
Bu hocam, bu copying
Yes.
konusunda. Şimdi burada toSpace'te kendini gösteren veya hiçbir tarafı göstermeyen olanları siliyor mu? Yani garbage collecting'i nasıl yapıyor burada?
Okay. So this is what you have currently. So from space is what you are currently working on. This is your heap. So this part of the heap is the only that you have. So this is the heap. Then this part is just is set aside for only garbage collection purposes. Okay. So what you do is very similar to the other algorithm. You start from your root, and then you look at all your live cells. And then whenever you find a live cell, for example, this one is going to be a live cell because from the root, in this case, there is only one root, right? And then from this root, I can reach this to this guy. So what it does is actually it takes this and copies it here. This entire cell is copied here. Okay, very simple. Okay, then now in this cell, I have 2 pointers. I need to check this one, of course. I know that this cell is actually pointing to those 2 pointers. And then I go for the first one. And then now this is A. Just for the time being, I'm just going to do copying of the A, the cells. And now this is going to be the B cell. And then I have the second one here, and this is the C cell, right? And then I have another one here. This is the D cell. And now I have this guy here. This goes back to the A cell, and I will have somewhere I'll have a mark saying that actually this is already copied, so that I can actually prevent the recopying of A. Okay, so I have now A, B, C, D. Now, of course, these addresses are wrong now. First of all, root now should be pointing to this guy, right? And A's first part should be pointing to B. And A's second part, this one, should be pointing to C. Right? I have to do this. But I can do them because I know where I copied them. And I can just go through those references and update those references. This is the algorithm. This is Chinese algorithm. It's a very simple algorithm. And then once I am done, now I can disregard this one now. I can say, okay, forget about this. Now this is my heap. The other half is gone. Now this becomes, for the next iteration, this becomes the from space. And this becomes the to space for the next iteration. You got it?
Anladım gibi hocam. Peki mesela garbage collecting yapacağı zaman nasıl yapıyor onu? Yani mesela burada örnekte yok sanırım ama mesela dışarıda bir yere point etmeyen bir
Okay,
tane
let's
parçayla.
put one here. This is the example that we had, right? So this cycle, this goes here and this goes here. Now, since this is unreachable from any root, right? This is going to stay here, there. That's it. It's not going to be copied here. This
Anladım.
D and
To
F.
space'e gitmiyor, from'da kalıyor. O zaman siliniyor.
Exactly.
Tamam.
So you can see that this is good for fragmentation because I am actually copying it one after another. And since I'm following the kind of the data structure anyway, this actually gives me also, let's say if this is this looks like a tree, right? No, it's not a tree, it's a graph. But anyway, the traversal of this graph is going to be similar, is going to be actually retaining some sort of locality of reference anyway. So this is also good from that perspective. Okay, any other questions? All right, thank you for your interest, and I'll see you on Wednesday. Hold on a minute before I forgot what I am going to say, and we'll continue with procedures and functions. Yes.
Hocam kaçırdım mı bilmiyorum ama midterm'le ilgili net bir şey diyecektiniz sanki.
It's going to be a homework. I'm not going to have a midterm.
Hocam tarih olarak?
We have. I mean, we are going to increase the number of homeworks by 1. That's it. And I'm going to take one of those as a midterm, and I'm going to tell you which one it is.
Thank you.
Okay. All right. See you on Wednesday then. Have a nice day.